Good afternoon. I'm Daniela. I'm a postdoc in the University of Aveiro, and this work is related with the titanium influence of the electrochemical reduction to iron from iron oxide-based ceramics. So iron production is a crucial step for steelmaking. However, the main route of iron production still consists in the blast furnace. So mainly they use iron ores inside of blast furnaces that can go until 2000 Celsius degrees. And during this, in this blast furnace, what happens is there's a carbothermal reduction of the ore until metallic iron. And in all these steps, we have a lot of generation of CO2 emissions. And this traditional route accounts as 70% of the worldwide production technology. So we need to find alternative ways to produce iron and steel without these CO2 emissions. So one of the possible ways of obtaining iron is by the electrochemical reduction in alkaline medium. So we use, in this case, sodium hydroxide electrolytes up to 80 molar. And we can use much lower temperatures than the traditional route. We can work from room temperature until 100, 110 Celsius degrees. Here you can see a typical electrochemical cell. It's a 3-electrode cell. It's a Teflon cell because of the strong alkaline medium. And we also use a heating system. I have to highlight here that we can perform this reduction in 2 modes. We can reduce the iron oxides into metallic iron by a solid piece. We call it bulk. It can be iron ore, it can be a hematite piece or whatever. And then we can also reduce by suspension. So we mix iron oxides in the electrolytes, and we use, for example, a rod, a steel rod, for example, as the working electrode. Because it's alkaline medium, sodium hydroxide, we always have water splitting. So these two are the only gases that we have produced in our system. We have hydrogen evolution in the working electrodes, along with the iron reduction. And on the counter, we have oxygen evolution. The only problem with the hydrogen evolution is because it competes directly with the cathodic current for iron reduction. So this eventually will decrease our efficiency. So how this mechanism works of reduction of iron-3 to metallic iron? Hematite, it's an insulated material. So it's not reduced directly to metallic iron. It undergoes several steps. Now I'm going to divide it into bulk, the pellets, and in suspensions mode. So the first step of the reduction of hematite, it undergoes to magnetite reduction. After magnetite, we have this reduction for iron 2A+ species that are going to be further reduced to metallic iron. This step, the reduction to magnetite, it's a crucial step because this occurs exactly between the current collector and the pellets and boosts the electrochemical reduction to continue to occur. In suspensions, on the other way, we have a dissolution because we have highly concentrated medium and also high temperature. So we have some dissolution to iron 3A+ species that are going to be further reduced to iron 2A+ species and later to metallic iron. This work is under the scope of Cedarwind European project. It's a project with several partners. And one of the partners, ArcelorMittal, it's a company in France. They just built a pilot scale for the electrolytical production of iron. At this moment in this pilot plant, they are only working with hematite as a raw material, as a feedstock for this production of iron. And Aveiro University, our research group, is one of the partners. And our job is to find alternative raw materials, alternative feedstocks that can be in future used in this pilot scale. So in this case, we are trying to study here this matrix between hematite and titanium dioxide and why. This matrix can be you can find it very easily in residues, in waste, such, for example, red mud waste that comes from the Bayer process. Of course, this is not the major phase. Titanium dioxide is not the major phase of this red mud waste. because it has hematite, alumina, silicates, but it still has more than 6% of titanium dioxide in its constitution, and also can be found in iron-rich minerals, for example, pseudobulkite. So in this specific case, we try to mimic this mineral that is rich in iron 3+. So our goal is to reduce pseudobulkite in this electrochemical reduction in alkaline medium into metallic iron, and we also want to study the impact of titanium during the reduction. So for this, we are going to study it in conversion in bulk, in pellets, but it's not just simple pellets. We process highly porous cathodes to study this reduction to metallic iron, because it has easy access of electrolytes into the pellets, and also facilitates the escaping of hydrogen. After this, we also study the suspension mode, because it's more feasible for the pilot scale. The design of the stellar microstructures was chosen by the emulsification method. So basically, we mix hematite with titanium dioxide in a water suspension with 50% of solids and with the dispersant agent, and we added liquid paraffin. Liquid paraffin is necessary to create these porous structures. So we have a burnout at 500 degrees. Of course, this releases CO2, but this is just at lab scale. So in future, this is not going to be used. Here, we just want to study the mechanism of reduction and how it works. For pilot scale, for sure, it has to be done by suspension mode. So this, in terms of burnouts and reactive firing rates, these are the rates used. For the pseudobulkite firing, we use 1,150 Celsius degrees. And in terms of analytical techniques, we use XRD, CM, EDS. We use porosity to study porosity by Archimedes method. And we also use cyclic voltammetry and chronoamperometry studies. So as I said, we use these two modes, the bulk in pellets and in suspension. However, in the bulk reduction, we compare it with hematite, highly porous hematite, and highly porous composites of pseudobulkite in excess of hematite, just for comparison purposes, and these occur only in bulk, not in suspension. So in suspension, we used only pseudobulkite powder. So in bulk, we have this pellet that was glued with silver paste to a nickel plate, and this nickel plate is going to act as current collector, and it was painted with lacquer. For suspensions, we use this pseudobulkite powder mixed with sodium hydroxide electrolyte, and we use a steel rod with a 1 square centimeter of area, and the iron is deposited here in this area. And this is exactly where iron is reduced in both cases. So we use sodium hydroxide and molar and 80 Celsius degrees. These are the design of the ceramic cathodes. The first image is the green monoliths of pseudobulkites after firing of the paraffin. It's very fragile, and you can see clearly the open porosities. We fire it until 1,150 Celsius degrees. You can see it's very porous still. It has interconnectivity between the pores and has an open porosity of 72%. We did the same procedure for hematite and for the composite, and we obtained around 56% of open porosity and 70% in the case of composite. The pseudobulkite is single phase, as you can see here. We have only segregation of hematites in the case of the composites, as expected. These are the cyclic voltammetry results. These give us really good information about at which potentials we have redox mechanisms, reactions occurring. So as you can see, we have 2 C peaks, cathodic peaks, and 2 A anodic peaks. So the cathodic peaks are associated with the reduction reactions. So first peak, we have reduction of iron 3 to iron 2 species. And C2 peak is not properly a peak, it's more like a shoulder. It's the reduction of iron 2 to metallic iron. However, this is exactly the region where we have hydrogen evolution. So that's why it competes for the cathodic current, because it occurs exactly at the same potentials. On the other side of the plot, we have two anodic peaks, which are associated with oxidation reactions. So the first one, we have oxidation from iron 0 to iron 2 species, and the second, iron 2 species to iron 3 species. This is the reduction of the porous cellular ceramic cathodes after 7 hours. So you can see the difference between the structure, the skeleton, before and after the reduction. You can see that the open porosity is still visible. You can see these pores, but the skeleton is covered by a spongy layer, as here is marked in blue, which is rutile and anatase. It's also possible to see these crystals. At first, we thought it was metallic iron. However, it is not. It is only magnetite. So it seems like we didn't succeed to obtain metallic iron at this cathodic polarization. So because of this, we increased the polarization to -1.30. And here we do have metallic iron. This is the dendrites of metallic iron, and we observe them only at the current collector. So here we can compare with the reduction of hematite and with the composites. You can see, as first thing that you can see is the difference between the hematite curve with the others. So it starts quite slowly. We have lower current densities, but increases sharply and after 7 hours. And in hematite case, we observe only dendritic metallic iron near current collector. This pellet was not completely converted to metallic iron. We still have some traces of magnetite and hematite far away from the current collector. And we used -1.15 volts as comparison. However, we have really low efficiency. And why? This is because we are using very high cathodic polarization for hematite. Usually we should use around -1.0808 volts. It's more than enough for increasing this efficiency. So this is, you can see directly the impact of hydrogen evolution during the reduction. So we did the same with the composite. Again, we didn't obtain metallic iron, only magnetite crystals. And when we tried to increase to -1.30 volts, you can see the cathode was destroyed, and this destruction was associated with hydrogen evolution. So only in these two cases, we have metallic iron. We also got metallic iron at -1.30 volts, but with lower efficiency because of hydrogen. So why we have such difficulty in obtaining iron with lower potentials? So as you can see here, this spongy layer, it's somehow covering these magnetite crystals. So it's kind of blocking these crystals to grow and to be reduced to metallic iron. So we believe that this titanium oxide works as a blocker of the reduction. So we also compared these results with the suspension mode. We apply the same potentials, -1.15 and -1.30 volts. You can see immediately the difference in current densities. This more cathodic polarization is clearly associated with hydrogen evolution. However, in both cases, we got metallic iron. We have here some magnetite phase, and this is just minor oxidation already after the deposition because it's exposed to air. It's very thin layer, so oxidizes quite fast. Here you can see the difference between the deposits. So we have a drop of efficiency from 25 to 5% when we increase the cathodic polarization, also again because of hydrogen. So in terms of conclusions, we can say that titanium species really do have a negative impact in the bulk electroreduction because we can really observe these non-conductive phases formation like rutile and anatase. They isolate the glow of the crystals and totally block the reduction. We have really low Faraday efficiencies because we needed to use high cathodic polarizations and hydrogen was affected. Hydrogen evolution also can destroy the cathodes, like the example of the composite. So in suspension mode, we obtain metallic iron. However, pseudobrookite doesn't look feasible to be used in the pilot plant scale. So also I have to say that the pseudobrookite has high content in titanium oxide. So in future, we are seeking to use lower materials with lower content of titanium, because probably it will not have such a strong effect. And we can mix it with iron oxides, hematite, or iron ore for improving the current efficiencies, and like this maybe it can be useful for the pilot plants. In terms of the ceramic cathodes that we observe rutile and unstructured anodized phases, this can open a new pathway for application as catalytic applications. Thank you all for your attention. I would like to acknowledge Sidron project and also remote project.
Thank you very much for good presentation.
Thank you.